Mhm.
Okay.
Mhm.
Shall we start?
Oh,
Yes, we can start.
Okay. All right. Thank you. All right. So let me go to my slides. Right. So this is joint work with Yanpeng Li at Sichuan University and Jiang-Hua at the University of Hong Kong. So my plan for the next hour and a half is the following. So first I'll review this notion of linearization from Poisson geometry, and then I'll apply this procedure to the standard Poisson structure on the on the Bruhat cells with respect to the Bott-Samelson coordinates. And then in the third section, we'll look at what happens if we apply this linearization procedure to a certain cluster algebra, to the initial clusters of a certain cluster algebra structure on a Bruhat cell. So the main result is that by doing so, we'll get an integrable system on a nilpotent Lie algebra. On the dual of that. And then I'll explain some byproducts, for example, the number of Casimir functions on a Bruhat cell with the standard Poisson structure, or on a nilpotent subalgebra with the Kirillov-Kostant Poisson structure. And in the last section, which in my view is the most exciting part of the story, so in section 3, we'll apply this linearization procedure to the initial cluster. So what happens if you apply this procedure to a general cluster? So do you have a notion of mutation of integrable systems? All right, so let's see. Sorry, what's that?
No question.
Okay, all right. So let's see how far we can go. So linearization. So I start with a Poisson manifold M, comma pi, and then suppose I'm given a point, so that the Poisson bracket the Poisson bivector vanishes at that point. Then on the cotangent space at that point, I can define a Lie bracket in this usual way. So suppose I have covectors alpha and beta. What I can do is I can choose locally defined functions f and g whose differentials at the point M are equal to alpha and beta, and then I define the Lie bracket of alpha with beta to be, you first take the Poisson bracket of the two locally defined functions, you get another locally defined function, and then you take the derivative of that at the point M. And then the assumption that pi vanishes at the point M guarantees that this Lie bracket is well defined. So the cotangent space is a Lie algebra. And then as a consequence, the tangent space, being the dual of the Lie algebra, comes equipped with a Kirillov-Kostant Poisson structure, which we denote by pi kk. So it's a very simple construction. For us today, we'll apply this construction to Bruhat cells. So what I mean is the following. So I start with the semi-simple group G. For me, it's always over the complex numbers, but the underlying field doesn't matter that much. And then you choose the standard structures. So B plus minus are opposite Borel subgroups. U plus minus are the maximal unipotent. T is a Cartan. And then this German G is the algebra of the group, and then you have a triangular decomposition. And then the vowel group is the quotient of the normalizer of the Cartan inside G by the Cartan. And then for any element small w of the vowel group, there's the corresponding Bruhat cell BWB mod B. On this Bruhat cell, we have the standard Poisson structure. So actually on the flag variety G mod B, we have the standard Poisson structure, and every Bruhat cell is a Poisson submanifold. And then some known facts are the following. So if you evaluate the standard Poisson bivector at the central element of the Bruhat cell, so WB mod B, this is equal to 0. Therefore, you can apply the procedure of linearization to the Poisson manifold BWB mod B with the standard Poisson structure at this point WB mod B, and then you got a Lie algebra on the cotangent space, and so a Poisson structure on the tangent space, and some simple computation, and just some simple theory of homogeneous Poisson homogeneous space tells you that the tangent space with its KK Poisson structure is isomorphic to the dual of the Lie algebra, which I call NW, equipped with its own Kirillov-Kostant Poisson structure. And here this Lie algebra NW is defined in this way. So you take all those positive roots alpha, such that when you apply W inverse to that, you get a negative root. And then you take the root space of negative alpha for all such alpha. Okay, so that's what you get if you apply sorry, yes.
Can you ask one question?
Yes, please.
What is standard Poisson structure on Bruhat cell?
Oh, sorry. So yeah. So you take the standard R matrix. So so for each let's say positive root alpha, you choose a root vector E alpha, and then F alpha for negative of that root, and then you take E alpha YHF alpha and the summation over alpha. That's a standard R matrix, and then you have a left invariant bivector field whose value at the identity element is the standard R matrix. You also have a right invariant bivector field whose value at the identity element is the R matrix, and then you take the difference of the two.
The whole group. Not the whole group, and then you receive it to the cell.
Is it in a whole group and when restricted to a Bruhat cell?
Sorry, can you say it again?
So you describe some structure on the whole group G, and then restricted to a Bruhat cell.
Oh yeah, sorry. So okay, so you have a Poisson structure on the group G, and then this Poisson structure descends to G mod B. And then each Bruhat cell is a Poisson submanifold. Or you can do it the other way. So so for each Bruhat cell, BWB inside G is a Poisson submanifold, and then you portion out by B. Yeah. Okay, great. Are there any other questions?
And when you take it together with Kirillov-Kostant structure, you first linearize the standard one, yeah?
Yes.
Because it's on group, it's quadratic, right?
It's not quadratic. Not quadratic.
The standard one.
The standard is not quadratic. In type A, it is.
In type A, yeah. I mean in type A.
Yeah, in type A, it is quadratic. Yes.
Yes, and then you take it linearization or not?
Yeah, you linearize that. Yes. Okay, great. Are there any other questions? Okay. So then we can move on. All right. So then I'll review some algebraic geometry about Bruhat cells. So these are called Bott-Samelson coordinates. So what I do is the following. So I start with a reduced word for the Val group element W. So this reduced word is SI1 times SI2 times ... all the way out to SIN. And then for each J between 1 and N, I choose a lift, so Sij dot of the simple reflection Sij to the normalizer of the carton. So here, let us recall that the vowel group is a quotient of the normalizer by the carton. So this is an element of the quotient. So and then this line with a dot is a lift to the normalizer. In particular, Sij dot is an element of the group G. Okay, and then for each j, I can also choose a root vector Eij for the simple root alpha ij. And then I can define the following map from C to the n to the Bruhat cell, sending the tuple x1 through xn to this complicated expression. So what you do is, so let's look at this. Let's look at this this part of the expression. So you multiply the root vector ei1 by this complex number x1, and then you exponentiate. So you get something in the group. And then you multiply with this lift si1 dot. That's also an element of the group. So this product is an element of the group. And then for each simple reflection in this reduced word, you do the same thing, and then you multiply them according to the order that the simple reflections appear in the reduced word. Okay, so so this is some map. If you haven't seen it before, well, it's probably complicated, but it is what it is. And the fact is that this map is an isomorphism of algebraic varieties. So in particular, this is a way of realizing the Bruhat cell as an affine space. And then the coordinates x1 through xn are usually referred to as the Bott-Samelson coordinates on the Bruhat cell. Then via this isomorphism, I get an algebra isomorphism from the coordinate ring of the Bruhat cell to the polynomial ring. And moreover, the standard Poisson structure on the Bruhat cell translates to some Poisson bivector field on the polynomial ring, and then the action of the carton on the Bruhat cell by left multiplication translates to some action of T on the polynomial algebra. All right, so so then from now on, we'll work on this polynomial ring. And then some facts about this polynomial ring. So if you put everything together, so this polynomial ring together with the standard Poisson structure and the T action, this is what is called a symmetric Poisson CGL extension. Okay, so that's just some terminology. What that says is really the following, the second bullet point. So for every symmetric Poisson CGL extension, there's a cluster algebra structure on the polynomial ring, which is compatible in a certain sense with both the Poisson structure and the T action. Okay, so what do I mean by that? So that means that you can find a cluster algebra structure on this polynomial ring, such that if yj are your initial cluster variables, and then you have the following conditions. So first, the initial cluster variables are log canonical with respect to the standard Poisson structure. So which means if you take the Poisson bracket of yi with yj, you get some constant multiplied with yij. So this is what compatibility with the Poisson structure means. And then compatibility with the T action means that each yj is an eigenvector for the T action on the polynomial algebra. Okay, so in
sorry.
Yeah.
And who are these deltas? These are some minors of your matrix.
Yeah, these are generalized minors.
How do you define these coordinates?
How do I define what?
Yg is your cluster coordinate, right?
Yes, these are my initial cluster variables.
And so in these variables, these are some minors of the.
Yes.
These are some minors.
Yes, it's as written. Is this?
And so And you say that they obey logarithmically constant Poisson bracket with some skew symmetric. Yeah, that corresponds to the R matrix Poisson structure. What is the relation of these variables with the Fock-Goncharov coordinates?
What are the Fock-Goncharov coordinates?
Well, it's in a sense similar. They also they construct the cluster structure on the Bruhat cells or double Bruhat cells in a Lie group, and the Poisson bracket looks very similar. This matrix of the Poisson B vector is usually integer valued or half integer valued. And they have some procedure of constructing the cluster quiver for this Poisson structure. But they are not minors, so, your minors look a little bit more to this Fomin-Zelivinsky variables, right?
Yes, yes, yes.
And in Fomin-Zelivinsky approach, it's not a Poisson bracket, but rather some two form is preserved by cluster transformation. So can you comment on that?
Okay, so I have to confess that I don't know much about the Fock-Goncharov story of class algebras. So here in our situation, what happens is that if you know these omega ij's, so these coefficients for the log canonical Poisson bracket, and you also know the eigenvalues for the yj's, and then that uniquely determines the initial mutation matrix. So in a sense, it's rather similar to Fomin-Zelivinsky. But other than that, I'm not aware of a more precise connection.
Maybe you can give some explicit example of some simple group where we can just see how much it is similar to what I mentioned.
Sure. So okay, I do have some examples down here. Yeah, so here, this example. So here I'm taking G to be SL3, and then W0 is the longest element of the vowel group. And then for a reduced word, I choose S1, S2, S1. Okay, so then by my definition, so maybe I should go back and explain what this Yj is in words. So you first, okay, so in my definition of the Bott-Samelson isomorphism, I have this very complicated expression, and then in the definition of Yj, what I do is I truncate this expression at position j. So I truncate at position j, and then I get some element of the group, and then I apply the generalized minor to that element, and then I get a number. This number is my Yj. So if I apply this construction to this particular example of SL3, so for Y1, I get the generalized minor omega 1 comma omega 1 applied to this expression. And it's very easy to compute what this expression is. It's just this matrix. And then the generalized minor delta omega 1 is just a principal 1 by 1 minor. So it's a top left entry. So it's equal to x1. Okay, and then you compute y2. So you just you truncate at position 2. So this is a product for position 1. This is a product for position 2. You multiply them, you get this matrix. And then the generalized minor delta omega 2 comma omega 2 is the principal 2 by 2 minor. So it's a determinant of the first two rows and first two columns. And it's easy enough to compute that this is equal to x2. And then the last one, which is the most interesting one, so you truncate at position 3, and then so here is what we get. by multiplying the first two positions and then the last position. You multiply them, you get this matrix. And then we are computing the generalized minor delta omega 1 comma omega 1. So again, this is the top left corner. So that's the into x1, x3 minus x2. So that's what our initial class of variables are in this simple example. Yeah. Right. So yeah. So maybe someone in the audience can comment on whether that's the same as formula. Sorry, I can't hear.
The question was, what is generalized minor?
Sorry, what is?
Generalized minor.
Oh, the generalized minor. Yeah, sorry. So yes. So where do I have some space? Okay, so I write it here. So suppose you have an element G of the group G. Okay, and then suppose that you can write it as let's say G minus G0 G plus, where G plus is in U, G minus is in the carton, and G minus is in U minus. So the Gauss decomposition. Okay, so then so this generalized minor applied to G is it's just the following. So so you apply G well, how do I say it? So G naught is an element of the torus. So you just do this. So what I mean is that omega I is a weight, so that defines you a character from the carton to the non-zero complex numbers. So T goes to T to the omega I. And then if you can decompose your element G in this way, you define the value of the generalized minor on G to be just this. And then one can prove that this map extends to all of G as a regular function. So in type A, yeah.
Thank you. Okay. You wanted to say what it will be in type A, yes?
Sorry, are you asking what they are in type A?
Yeah, you wanted to.
Right. Right. So in type A, what you do is you just take the top left minor.
Okay.
You take the top left principal submatrix and then take the minor of that.
Okay.
Yeah.
It's a bit hard to understand in such way, but you gave an example for SL3, so you have there three variables, yeah. And what are the Poisson brackets? What is this matrix of the Poisson structure in these variables in SL3 case?
I don't know. I have to compute.
So it's not easy, yeah. Okay.
It's not easy, right? Yeah. Okay. Do we have further questions? All right. So then let's move on. Right. So where are we? Right. So we had this procedure called linearization, and then we had this open Bruhat cell. And then we explained the Bott-Samelson coordinates on the open Bruhat cell, and then we translated everything to the polynomial algebra. So yeah, so I was explaining these facts. So the first bullet point says that the polynomial ring with the standard Poisson structure and the torus action in the symmetric Poisson CGL extension. And then the second bullet point says that every symmetric Poisson CGL extension has a cluster algebra structure which is compatible with Poisson and T action. And then combining these two bullet points, we get a cluster algebra structure on this polynomial ring whose initial cluster variables are the yj's as written. Okay, so now the question is, okay, we can apply the linearization procedure to this algebra together with the standard Poisson structure. Now, can we apply this linearization procedure to the initial cluster variables? Or can we make sense of that? And if we do that, what do we get as a result? Okay, so I need some preparation for that. So for each j between 1 and n, I define a positive root lambda j to be si1 times dot dot times sij minus 1 applied to alpha ij. In other words, if you put the roots lambda 1, lambda 2 up to lambda n in the sequence, so these are precisely, sorry, maybe as a set, these are precisely all those positive roots alpha, so that W inverse alpha is negative. Okay, so this is related to how I define this algebra and this Lie algebra and W minus. So this is all the root spaces G negative alpha where alpha satisfies these conditions. Okay, so then for each such positive root lambda j, I can define a corresponding root vector. So what I do is I start with this chosen root vector for the simple root, so eij, and then I apply the adjoint action of the simple reflection, I mean the leaves of the simple reflections. And then you can easily check that this is indeed a root vector, and the corresponding root is lambda j. Okay, so then, as I said, so the lambda j's are precisely all those alpha, so that W inverse alpha is negative. So I can define a vector space isomorphism from C to the n to NW minus star by sending x and the tuple x1 through xn to this expression. So for each of my root vectors, I multiply by xj. Oh, sorry. So I forgot to say that I'm identifying NW minus dual with NW via the killing form. Okay. So now I have two isomorphisms. So this one as displayed is an isomorphism of vector spaces. But let us also recall that we have a Bott-Samelson isomorphism from Cn to the Bruhat cell. So this is Bott-Samelson. All right, so then via this isomorphism of vector spaces, we can regard this polynomial ring also as a coordinate ring of the dual of the Lie algebra. And then I can make the most important definition. So for each j between 1 and n, I define yj low to be the lowest degree terms of my initial cluster variable yj. Okay, so what do I mean by that? So each yj is a polynomial in the variables x1 through xn. As a polynomial, it's not homogeneous, but I can take all those summands in yj whose degree is the lowest possible, and then I take the sum of those. That's my yj low. Okay, so then yj was a polynomial on the Bruhat cell. Another way I view yj low is I view them as elements in here in the coordinate ring of the dual of the algebra. Okay, so this is what I mean by linearizing the initial class of variables. Okay, so this is not really linearization, it's really taking lowest degree terms. But anyway, that's what the definition is. All right, so then for each j, we had a function yj low. So now we have n functions on the dual of the Lie algebra. And then our main theorem says that any maximal algebraically independent subset of my yj lows is an integrable system on the dual Lie algebra with the Kirillov-Kostant Poisson structure. In other words, when you linearize the Bruhat cell with the standard Poisson structure, you get the dual Lie algebra with the Kirillov-Kostant Poisson structure. And then when you further linearize the initial cluster variables, you get an integrable system on the dual space of the Lie algebra with the Kirillov-Kostant Poisson structure. Okay, are there any questions about the statement of the theorem? Okay, excellent. So let's look at some examples. So first, let's go to our type A2 example. So we have already computed the initial cluster variables y1, y2, y3. So let's take the lowest degree terms. So y1 is a degree 1 polynomial, so y1 low is just x1. And then y2 is just x2, so y2 low is also x2. But then y3, sorry, go ahead. Oh, was there a question or comment or something?
No.
Okay, yeah, sorry. So, okay, so y3 is x1, 3 minus x2. So the lowest degree term is negative x2. Okay, so in this example, our y1 low, y2 low, y3 low are x1, x2, and then negative x2. So it's easy to see that, for example, you can choose x1 and x2 as a maximal algebraically independent subset of the set, and then they do form an integral system with respect to the Kirillov-Kostant Poisson structure. So this is because x1 is here, x2 is here, and x3 is here. So with respect to the Kirillov-Kostant, or with respect to the standard Lie bracket on upper triangular matrices, these two root spaces bracket to 0. Okay, so in that example, everything is simple.
By integrable system, you mean just a set of Poisson commuting functions with respect to Kirillov-Kostant bracket,
and also the number of function algebraically independent functions is the correct number. So on a symplectic
but how do you here count the correct number?
Right. So on a symplectic manifold, the correct number is half the dimension, and then on the Poisson manifold, the correct number is the number of Casimir function, algebraically independent Casimir functions plus half of the dimension of the maximal coadjoint orbits.
But here, what is the orbit here?
The coadjoint orbits.
But but which one? So this is an integrable system, you say, with respect to Kirillov-Kostant bracket on which orbit?
No, not on a particular orbit, on the dual Lie algebra.
On the whole?
Yes. So here x2, it turns out that x2 is a Casimir. So let me draw the matrix one more time. So you see that x2 corresponds to the highest root. And the highest root space Poisson commute with every other positive root space. So x2 is actually a Casimir. And that's actually the generator of the Poisson center. So this the Dural-Lie algebra is a three-dimensional space. We have one Casimir, so the maximal dimension of the coadjoint orbit is equal to 2. So so on each coadjoint orbit, we need one function in an integral system. So in total, we need 2, one on each leaf and then one Casimir. And for this example, our integral system is x1, x2. Okay, so are there any other questions? All right, so then let's maybe look at a more interesting example. So if G is SL6, and then W again is the longest element, and for a reduced word, I choose this line, which I usually refer to as the standard word. What I do is I multiply 1 through 5, and then 1 through 4, and then 1 through 3, and then 1 through 2, and then 1. It's easy, or it's known that in type A, this is always a reduced word for the longest element. And then you can compute the Yj lows. You can write down formulas for them, but there are too many of them to write down. But okay, so but it's easier to draw a picture for them. So so for the Yj lows, we have the following functions. So first, the entries in the blue 1x1 squares are some of our Yj lows. And then the determinant of the green 2x2 submatrices, so we have 3 of them, are also examples of our Yj lows. And then there's one 3x3 orange square, and the determinant of that is also one of our Yj lows. Okay, so so the claim is that all such functions form an integral system on n star, sorry, on n minus star. Okay, so maybe let's make sure that the dimension is correct. So the dimension of n minus star in this case is 15, because the dimension is just the length of the longest element. You can easily count that we have 15 simple reflections for our reduced word. And then the Casimir functions, so the Poisson center So it turns out that the Poisson center in this case is a polynomial ring generated by okay, so maybe I should put it this way. I have a 6x6 matrix. The Poisson center are the following. So the highest root space, as we discussed, is a Casimir. And then I can also take the top right 2x2 corner. The determinant of that is another Casimir. And then I can take the top right 3x3 corner. That's also a Casimir. So I have 3 of them. And it turns out that the Poisson center is a polynomial algebra generated by these 3 Casimirs. Okay, so we have 3 Casimirs. So it turns out, so as a consequence, the dimension, so the maximum of the dimension of symplectic leaves is 15 minus 3, so that's 12. So 12 dimensional, so on each of them I need 6 functions in an integral system. and then I need to add 3 because my Poisson center contributes 3 functions. So altogether, I need 9 functions in an integrable system. And then if you count the number of squares in my picture, you'll see that it's 9. We have 5 blue squares, 3 green squares, and 1 orange square. The sum is 9. Okay, and you also see that these 3 generators of the Poisson center are actually parts of our integrable system. Okay, so are there any questions so far? Or comments?
Is it possible to distinguish in your construction the Casimir and Hamiltonians?
Sorry, I didn't hear you clearly.
From your construction, is it clear what is Casimirs and what are Hamiltonians?
Right. So okay. So later I'll state a theorem explaining what the Poisson center of NW minus star is. This is a consequence of our construction. It's not immediately clear. There's some work that one has to do.
Okay. Thank you.
Yeah. Yep. Are there any other questions?
And sorry, and you just consider these integrals which are in the involution or Casimirs with respect to Kirillov-Kostant Poisson bracket, right?
Sorry, the Casimirs with respect to the Kirillov-Kostant Poisson, yes.
And the integrals of motion also, they are in the involution with respect to Kirillov-Kostant bracket, or
all my functions are Poisson commutative with respect to the Kirillov-Kostant Poisson structure.
And so where is this other Poisson structure in your picture, which you
the standard one?
You in the integrable system, I mean.
Sorry, which other Poisson structure? The standard one.
You said, yeah, the standard one.
I mean, that's my starting point. The whole point of the standard one is that, okay, for the standard one, I have a compatible cluster algebra structure, and then I can linearize the standard one to get the Kirillov-Kostant, and then I can linearize. Yeah, I can linearize.
You say that just Kirillov-Kostant it is Kirillov-Kostant, which is this linearization.
Yes, exactly. Okay, great. Okay, are there any other questions? Okay, excellent. So then let's move on. Right. So then let me spend some time. Let me spend some time explaining why my functions Poisson commute and why we have enough algebraically independent functions. So so for Poisson commutativity, this is a cute but very simple argument. So the first observation is that the Kirillov-Kostant Poisson structure has degree -1, in the sense that if I have homogeneous polynomials f and g of degrees A and B, and then their Kirillov-Kostant Poisson structure, Poisson bracket is homogeneous of degree A plus B minus 1. Okay, then the second observation, which is a direct consequence of linearization, is that I can decompose the standard Poisson structure as the Kirillov-Kostant plus some higher degree terms, where by higher degree terms, I just mean those bivector fields whose degrees are bigger than or equal to 0. Okay, so KK has degree -1 by the first observation. And then the third thing that we need to use is that the YJs with respect to the standard Poisson structure are log canonical, as we explained above. So then let's, yes. Oh, sorry. Okay, so then let's look at this equality in more details. So what can I say about the right hand? What can I say about the right hand side? So this is the right hand side. And I asked myself, what is the lowest degree term of that? Okay, so omega omega jk is just a constant. I don't care about that. So the lowest degree term is the lowest degree term of yj times the lowest degree term of yk. So that's why this sign is the lowest degree term of the right-hand side. And then what can I say about the left-hand side? Okay, so first, by the second observation, to look for the lowest degree term of the standard Poisson, I need to look at the lowest degree term of the KK Poisson. Okay, but then yj and yk have their own lowest degree terms, so yj low and yk low. So the possibly lowest degree term of the left-hand side is a KK Poisson of yj low with yk low. But then using our first observation, the KK Poisson of yj low with yk low has degree, this expression. Okay, so pi kk has degree -1. Okay, but then you compare the left-hand side with the right-hand side, you realize that this term, the degree of this term is too low for the equality to hold, right? So this is the degree of the lowest possible degree terms of the right-hand side, but this is too low because of the -1. So the only possibility is that this whole thing equals 0. Okay, so yeah, so that's a very simple argument, and it shows that whenever we linearize the initial cluster variables, and the lowest degree terms automatically Poisson commute. Just for this essentially trivial reason. All right, so and then why do I have enough algebraically independent functions? So for this, I have to use some sophisticated structures of Poisson CGL extensions. So what turns out to be the case is that for any j, if I look at the jth initial cluster variable yj, I can write it in the following way. So first, I have a term which contains xj. So it's of the form xj times yj minus. So you don't need to know the meaning of j minus. It's just some index which is strictly less than j. And then plus some other term. And the key point is that yj minus and delta j applied to yj minus are both polynomials in the variable x1 through xj minus 1. So xj does not appear in those two polynomials. Okay, so as a consequence of that, if xj times yj minus low, so in other words, the lowest degree terms of the first summand appears in yj low, then it is algebraically independent of the yi lows that appear before yj. Okay, simply because this variable xj does not appear in y1 through yj minus 1. Therefore, if the degree of yj low is equal to the degree of yj minus low plus 1, namely this term does appear in yj low, then yj low is independent of the previous ones. Okay, so then what this counting tells us is that so for each simple root alpha, if I denote by j alpha the index or the position where the simple reflection as alpha appears for the last time in the reduced word for w, for this reduced word w, then this expression is the least number of algebraically independent functions. Okay, am I clear about that? Or am I still connected?
Yeah.
Okay. Okay, right. Okay, so maybe let me repeat. So so for each simple root alpha, okay. So we have this reduced word on W, which is SI1, SI2, SI3, SI4, SI5, just to write a few. And then S alpha may appear at some places. For example, this is S alpha, this is S alpha, and then suppose I have more, and this is S alpha. Okay, so so if I take J to be say 7, so this position is J, this is J minus, this is J minus minus. Okay, so I'm saying that by this argument that I just explained, if the degree of say Yj minus is the degree of Yj double minus plus 1, then the fourth y variable, I mean the low of the fourth y variable is independent of the previous 3. And if the lowest degree of Yj is 1 plus the lowest degree of Yj minus, then this Y7 low is algebraically independent of the first 6 Yj lows. Okay, therefore, for each such sequence, so for each alpha, S alpha appears at some places. So for each, I mean for how do I say it? For each set of indices where a given S alpha appears, the least number of algebraically independent functions that you can see in this sequence of Yj lows is the degree of the last of them. So in this example, the degree of Y7 low is the least contribution of algebraically independent functions among Yj minus minus, Yj minus, and Yj. Okay, so in total, for each simple root alpha, you take the degree of, you take the sum of all these expressions as the least number of algebraically independent functions in our integrable system. Okay, so then the next step is to find an explanation for this number. So it turns out that the following is true. So if we look at the open Bruhat cell together with the standard Poisson structure, the action by the Cartan subgroup actually respects the Poisson structure. In other words, the T action on the Bruhat cell is an action by Poisson automorphisms. Therefore, it makes sense to speak of T leaf. So a union. Okay, so a T leaf is a union over small t in T of a T translation of a symplectic leaf. Okay, and by some standard results in Poisson geometry, we know that every Bruhat cell contains an open T leaf. Therefore, it makes sense to speak of the T Poisson Pfaffien, which I denote in this way. So by definition, this is the following expression. So you can take pi st wedge with itself the maximal number of times. Okay, so let me stress that the standard Poisson bivector is a bivector. So when you wedge pi st with itself, you don't necessarily get 0. Okay, if you have a vector, you wedge with itself, you get 0 certainly. But pi st is a bivector. So when you wedge with itself, you don't necessarily get 0. Okay, so now you wedge pi st with itself the correct number of times. So the number of times is actually half the dimension of the maximal coadjoint orbits. And then you take the wedge product with the directions coming from the T action. Okay, so I don't know how to write it. So I'll just write T action. So that's my definition of the T Poisson Fafien. So here by the T action, I mean, so by definition, the T leaf consists of two directions. One is the direction of the symplectic leaf, and then this part is tangential to the symplectic leaf. And then there's also a transverse direction given by the T action. Okay, so then for each element of the Lie algebra, you get an infinitesimal action, or you get a vector field on the Bruhat cell. You choose a basis for the transverse direction, then you get some vector fields, you wedge them, and then you take this very big wedge product. This is independent. Well, this is well defined up to a multiplicative constant, because this is actually a top degree section. Sorry, this is an anti-canonical section. So it doesn't matter how you choose the transverse direction. And then it turns out that if you write the T Poisson Fafien, or if you expand the T Poisson Fafien with respect to the wedge of the partials of the Bott-Samelson coordinates, you have some polynomial coefficient. This polynomial coefficient turns out to be the product of those initial cluster variables y, j alphas. So remember, this j alpha is the last place where s alpha appears in my reduced word. So it's why j alphas are the last appearance cluster variables. In other words, these turns out to be the frozen variables in my cluster algebra structure. Okay, so this is probably very technical if you haven't seen this before, but the upshot, or what you should take home with you, is that if you expand the T Poisson Fafien with respect to the wedge of the partials of the Bott-Samelson coordinates, the coefficient you get is a product of the frozen variables. Therefore, this number that we were interested in is just the degree of the lowest degree terms of the coefficient. Okay, and then you can make use of this to compare with the top, the highest possible wedge power of pi kk with itself. There are some details to be checked, and I don't want to do it now. But the whole point is that the way to determine the correct number of algebraically independent functions in our integrable system is to look at the degree of the coefficient of the T Poisson Fafien. Okay, are there any questions?
No,
Sorry, what's that?
no, it's clear.
Okay. Okay, is everything good?
It's more or less clear, yes.
Okay, great. All right, so yeah, so that's our main result and a brief explanation of how to prove it. And then here are some byproducts. So the first line is the following. So for any finite dimensional Lie algebra, so in our case, we are interested in this Lie algebra and W, one can define its index, right? So the index of any, sorry, sorry. So the index of any Lie algebra G is the minimum of the dimension of the stabilizer of C, where C runs over all the dual of the Lie algebra. So this is a very classical definition, and a very a seemingly innocent question is, what is the index of this Lie algebra NW? Okay, so for example, for a semi-simple Lie algebra, the index is nothing but the rank, right? So for this Lie subalgebra NW, what can you say about its index? Okay, so this seems an easy question, but I asked many experts, but no one seems to know the answer. But then as a consequence of our theorem, we cannot give a formula for this number. So if we write dW for the degree of the lowest degree terms of the coefficient of the T Poisson Pfaffian, then the index is just this number, twice of dW minus the length of W. And then let me remark that the length of a Val group element is always easy to compute. And then dW's number, dW is the lowest degree term of FW, I mean the degree of the lowest degree term of FW. But as a remark, to compute this, you just need to compute the frozen variables and then take the lowest degree term of those. Okay, so this is also computable. So the first byproduct of our theorem is a computable expression for the index of the Lie algebra NW. So in particular, if you take the Lie algebra NW naught, which is just n, and then you can ask, what is the index of n? Okay, so this is actually this is known due to the work of Kostant. Kostant says that, so Kostant defines the notion of cascade. So Kostant says that there's a very special subset of the set of positive roots, which is called the cascade of roots. So you take the cardinality of that set. This is equal to the index of n. So in the special case where W is equal to W naught, our theorem agrees with Kostant's result. Okay, so that's the first thing we can say. And then the second thing we can say is the following. So whenever you have an integrable system, a very natural question is, what can you say about the integral of motion? Or in other words, what can you say about, for example, the generic fibers of this integrable system? So what we can prove is that the Hamiltonian flows of our integral system is always complete. Okay, in the sense that for every function in our integrable system, so suppose we have fj low, and then you can take the Hamiltonian vector field of that function. Oh, sorry, it's not f, it's y. Of our function, so that's a vector field on NW. Then you can try to solve for the integral curve, and our theorem says that this integral curve is defined for all time. Maybe okay, already here. So the integral curve for this is defined for all time. So in principle, the integral curve of a vector field with a given initial condition is only defined in a small neighborhood of 0. In our case, we can prove that you can solve this ODE for all time. Okay, so for the generic fibers of our integrable system, we believe that they are always isomorphic to affine spaces. At this point, we don't have a proof of this, but in special cases, we do have proofs and we believe it's true in general. Okay. So the next byproduct is, or this probably partially answers one of the questions before. So for our integral system, how do we know which function is a Casimir and which are the integral motions on the symplectic leaves? So to explain this, these results work only in the special case where W is the longest element W naught of the Bell group. So first, need the following notation. So negative W naught is always an involution of the set of simple roots. So this involution is denoted by alpha goes to alpha star. So alpha star is negative W naught applied to alpha. And then as a consequence of our work, we can make explicit the Poisson center of the open Bruhat cell for the standard Poisson bivector field, and also the Poisson center for NW star with the Kirillov-Kostant Poisson structure. So the result is the following. So in the case of the open Bruhat cell, the Poisson center is a polynomial algebra generated by either the Yj alphas. So remember, J alpha means last appearance of S alpha. Okay, so it's generated by those Yj alphas where alpha is equal to alpha star, or by the product of Yj alpha with Yj alpha star, where alpha and alpha star are not equal. Okay, so as an example, so if I draw the type A Dynkin diagram, so this is alpha 1, alpha 2, alpha 3. This is alpha r minus 2, alpha r minus 1, alpha r. So I suppose that everyone in the audience knows that this reflection star sends alpha 1 to alpha r, and alpha r to alpha 1, certainly. And then alpha 2 to alpha r minus 1, alpha 3 to alpha r minus 3, etc., etc. Okay, so then our theorem says that if I take the last appearance of 1, multiply with the last appearance of r, alpha 1, multiplied with the last appearance of alpha r, that's a Casimir function on the open Bruhat cell. And then I can also take the last appearance of alpha 2, multiplied with the last appearance of alpha r minus 1. And then similarly, alpha 3, alpha r minus 2, ... So those are Casimirs, and those freely generate the Poisson center. Okay. And for the linearized Poisson structure, so for n minus star with the Kirillov-Kostant Poisson structure, the situation is very similar. So we can define some elements of the root lattice, which we call prim alpha, prim for primitive. Okay, so and we can okay, so a fact is that this element prim alpha, however it is defined, is either equal to the weight of, so weight alpha means this is the T weight of Yj alpha. So this weight, this prime alpha is either equal to weight alpha or is equal to half of weight alpha. And in these two cases, we can take the following functions. And if prime alpha is weight alpha, then we take yj alpha low. That's a Casimir function on the linear for the linear Poisson structure. And if prime alpha is equal to half of weight alpha, it turns out that yj alpha low is a square of some polynomial in the Bott-Samelson coordinates. So then by the square root of this thing, I just mean a choice of a polynomial whose square is yj alpha low. So it turns out that those functions are Casimirs, and they freely generate the Poisson center.
So could you explain it on the example of A3?
Yes, certainly. So so in this A3 example, x1 and x2 are sorry. In this A3 example, x2 is a polynomial generator of my Casimir of my Poisson center.
Yeah, but how it follows from your construction? Of your previous,
Sorry,
how you get it from your previous construction?
yes, so you just apply this construction to that example, you get x2. Where is it? Right. So yeah. So it turns out. So okay. So it turns out that in this example we only have the first case. Okay. So prime is always equal to weight alpha, and never equal to half. Okay. So then you look at the last appearance of alpha 1 and of alpha 2. Okay. So in this example you have yj alpha 1 low, and then yj alpha 2 low. Okay. And then we go back to our example. Yes. So this is the last appearance of alpha 1. This is the last appearance of alpha 2. Yes.
Yes.
Okay. Okay. So then yj alpha 1 low is y3 low. Right? And then y3 low from our example is negative x2.
Yes.
Okay. Yes, and then yj alpha 2 low is y2 low, and this is x2. Yeah. Okay, great. So yeah. Right. So that's what our theorem says in that simple example. So to the best of my knowledge, this last theorem is new. So before us, there have been a lot of people who tried to identify the Poisson center of n minus w, so including Kostant, Joseph, and all of other people. I believe our theorem is the first explicit expression for the generators of the Poisson center. Okay. Okay. So are there any questions? Okay, excellent. So then we move on to the very last part of today's talk. So so here the key point is what happens to an arbitrary cluster. So let us recall that our starting point was a Bruhat cell together with the standard Poisson structure, and then we linearized that to get the Kirillov-Kostant Poisson structure, and we said, okay, so what happens if we linearize the initial cluster variables? Okay, so that's our yj's. And then when we apply this linearization procedure, we said, okay, we get a integrable system. Okay, now suppose that I have an arbitrary cluster, so sigma, which may or may not be the initial cluster. And then I can apply this linearization procedure to sigma in the sense that for each cluster variable in sigma, it's a polynomial in the Bott-Samelson variables, so it makes sense to take their lowest degree terms. Okay, so that's how I define this sigma low. And then the natural question is sigma low an integrable system? In other words, if I take a maximal algebraically independent subset of sigma low, is that an integrable system for the Kirillov-Kostant Poisson structure? Okay, so Poisson commute is clear. So it's the same argument. So if you go back to here, so to our explanation of why the low of the initial cluster variables Poisson commute, you will see that the key point is that with respect to the standard Poisson structure, they are log canonical. But actually, for any cluster, the cluster variables are log canonical with respect to the standard Poisson structure. So you can play the same game. You can run the same argument, and the conclusion is that sigma low consists of pairwise Poisson commute functions. Okay, so then the only question is, do we have sufficiently many algebraically independent functions in our set sigma low to form an integrable system? Okay, so our conjecture, well, we don't know the answer, we can't prove it, but our conjecture is that the answer is yes. We do have enough, sufficiently many algebraically independent functions. So suppose that the conjecture holds, and then what can we say? So we can start with an arbitrary cluster sigma. So here sigma, then I can apply a mutation of clusters. So I get another cluster sigma prime. And then for both sigma and sigma prime, I can apply this linearization procedure to get sigma low and sigma prime low. Okay, and this procedure of going from sigma low to sigma prime low can reasonably be regarded as a mutation of integrable systems. Okay, so then I guess the punchline is that if our conjecture holds, then it makes sense to speak of mutation of integrable systems on the linear Poisson structure, and then how do you package these things in a nice way? So does it make sense to speak of mutation of integrable systems? Okay, so the answer we don't know, and we don't know how to package these nice things. But what are some evidences for this conjecture? So I guess the easiest case would be the following. So if you choose a bipartite Coxeter element, whatever that means, so then you can concatenate this bipartite word, and then you almost always get a reduced word. Okay, so actually you get a reduced word if and only if your Lie algebra is not of type A1 or A2. So in most cases, this concatenation is a reduced word. And it turns out that the resulting cluster algebra structure on the Bruhat cell, on this Bruhat cell, is of finite type. Okay, so the advantage of this situation over the general situation is that since the cluster algebra is of finite type, there are only finitely many clusters, finite many cluster variables. So to verify that sigma low is indeed an integrable system is a finite problem. You need only verify finitely many clusters. Okay, so we did a lot of computations. So we were able to verify that our conjecture holds in types, let's say B2, G2, A3, and these are easily doable by hand. And then in type A4, we verified almost all clusters. And then in type A, we verified that for all first generation mutations, our taking low does give an integrable system. So here I wrote A sub 2s plus 1, so A sub an odd number, but it's just because I'm lazy. I didn't verify A sub an even number, but in principle, the verification is the same. And other than these finite type cases, we also verified this conjecture for many general cases with randomly generated mutations. And in all the examples that we have computed, sigma low is always an integral system. So that's some evidence that our conjecture holds true, but at this point we don't have an idea of how to prove it in general. So if someone in the audience has an idea about how to prove this, I'm very happy to discuss. Okay, so let me make some final remarks. So today, the structural cluster variables of a certain cluster algebra structure. But you see that in this argument, really the key point is that the initial cluster variables are log canonical. Okay, but there are many other naturally defined log canonical coordinates on a given Bruhat cell. So for example, the factorization coordinates. Okay, so the factorization coordinates are not necessarily polynomials in the Bott-Samelson variables. And in fact, they are in general rational functions, but still it makes sense to take the lowest degree terms. Okay, so if you have a rational function, you can take the lowest degree terms of both the numerator and the denominator, and then you take the quotient. And then by playing the same game, you can easily verify that when you take the lowest degree terms of both the numerators and numerator and the denominator, the functions you get are Poisson commutative. And in all the examples that we have looked at, we do have sufficiently many functions in our set to form an integral system. So our feeling at this point is that this construction is very general. As long as you start with a naturally defined log canonical coordinate system on a Bruhat cell, and then you apply our procedure of taking lowest degree terms, you most likely get an integrable system. But at this point, it's not clear to us how to formulate this in the correct way. In other words, to what generality does our procedure give rise to an integrable system? Okay, so I guess that's all I wanted to say. So thank you for your attention.
Thank you.
Thank you.
Thank you.
And in the simplest example you had with this SL3, yeah, when one Hamiltonian, one Casimir element, so the mutated integrable system will be just correspond to transposition of your matrix with respect to anti-diagonal.
A3. So in this SL3 example, so it's a type A2. And then in the type A2 example, we have 5 clusters, actually 5 cluster variables.
SL3, you have
SL3 is
just
type A2.
SL3, just 3 variables, no?
It's type A2.
A2, yes.
Yeah, so the finitely generated cluster algebra of type A2 has 5 clusters. Yeah, so and 5 cluster variables.
Okay, I just wanted to understand what is this mutated integrable system in
Yeah.
any simple terms, but since I
Yeah,
didn't get it, maybe everyone understood. So
no, sorry, I don't remember the formula.
Vadim, any questions in the audience?
No, I think,
So let's thank the speaker.
yeah.
Thank you.
Thank you.